group in San Carlos and the group of Randall Hewlett in Texas, which started about a decade ago and has been producing nice results ever since. But yet we have to go on and look for things more complicated like vortices and turbulence. For now, it will be about Faraday waves and how to go from there up to granulation, which is as far as we went. So essentially, it's a very simple outline, okay? So you don't get bored, I hope. It won't take long. But basically, I will speak about how you can use modulation of interactions in between the particles to experience these Bose condensates. And two applications of these modulations could be the study of Faraday waves, which we complete successfully, and the granulation, which I think we just started observing the results. And we have some ideas what's going on, but there's much more to come, I hope. So most of these results I'll be speaking about will be, you can find in here, okay? Okay, so the modulation of interactions in atomic BECS, okay, has been found to be widely tunable in several orders of magnitude if you find them and successfully control and tune them using a magnetic field, an external magnetic field adjusted in the proper way. The idea, as far as I can track, came from Kevrakidis and Adhikari early in 2000s, and basically they suggested that if you use this external magnetic field, you can tune the interactions, and you can do that sinusoidally or something different. We choose to do sinusoidally, and we got the results mostly by doing that, okay? So, okay. So, a while ago, we started that project. Actually, I was just coming back to the group, and so I knew from these results, mainly Vanderlei and other students started that a while ago. So they went directly to modulate the B field and try to find, and to excite normal modes of the superfluid. Basically, this quadrupolar, the lowest mode, and observed. This is the typical results they found, and they scanned this frequency of modulation here over a fairly decent scale here, and found a very large resonance around this plot here. And they scanned it basically around this area key. So, okay, it was very close to the zero resonance and not so large. So it was like a small modulation, let's say, so to speak. But anyway, you could go from the Thomas Fermi regime up to the non-interacting, and this is produces sort of very nice results here, which we started thinking about, and we decided, okay, maybe this was a starting point, but what, or maybe could we play a little bit more with that and go towards, for instance, turbulence or something like that, like if we go a little harder on that. And that kept going, and actually it is, yeah. It's a Fourier transform, the normalized one, as a function of the modulation frequency here, just showing the modes that you're exciting here. Usually you have a resonant mode and some other mode which appears together here. You want to comment on that, Vanderlei? Yes, which is coming from this mode which I showed you. Okay, basically that's it, along the actual direction, okay, which is what you're seeing here. So the stretching, compression. And this is as much as you can see here. Simple resonance on the normal mode. No. It's just verification of that is there, and that can be tuned and accessed by modulating the external magnetic field. Okay? So instead of trap modulation, which is the other way that people used to do before. So you compress your trap and relax, something like that. So you do that a bit more independently here without modifying the density. Yes? No, you do have a trap. Yeah. Yeah. Absolutely. The trap is there. It's just an optical trap. Single focus laser beam, okay, which is there. And that's the reason. If you're going to play with a magnetic field, if you have a magnetic trap, that won't work that well. I mean, okay? In this case, that is kind of the trick of this lab and this experiment, okay? Okay. In the following, I'm going to change the topic here. So, okay, we're going to use that kind of modulation, and we did it again a while ago. That the second part, which comprised of Faraday waves and granulation, it started like 4 years ago. So it took a long while to fully understand the thing or to understand it. But basically, we decided to do it again in a different regime. We decided to scan a little larger and regime of frequencies and amplitudes. And we started to see these Faraday waves taking place, which was kind of expected. For those of you that don't know, essentially, it was discovered about 200 years ago by Faraday himself by basically shaking a bucket, okay, and seeing what happens on the surface. You see these nice patterns forming on. Basically, they have a variety. These things depend a lot on the kind of fluid that you have, the driving amplitude, frequency, viscosity, all kinds of things you can think of. It was basically described by approximations of the Navier-Stokes equations. And it has been discussed that by doing so, you can go or undergo towards turbulence. So it has a good promise on that, which we eventually will go there, okay? So in superfluids, there's not many, there's tons of theoretical works on that, okay? So I'm not going to annoy you, but on the experimental side of that question, there are only 2 or 3 published papers that we know of that clearly show this pattern showing on the superfluid. This is in helium-4, and this is in atomic rubidium-87 condensate by Peter Engels and Abe from Japan. We think that it's a good idea to study this topic in superfluid because the damping is small, okay? So whatever you imprint, it will take a while to dissipate, and so there's not many ways to dissipate. So, but the mechanism may also be interesting to be studied. So we decided that could be a good idea to study, to keep this superfluids as topics. And it has been shown also that the modulated trap frequency, as it was done here, in a quasi 1D BEC, essentially showed as surface waves. It's a little bit different here because in a BEC you have to keep in mind that the depth of you don't have that much matter actually, or atoms in this. So it really goes to the thickness of the condensate, and you can see like it really interrupts. So that is a finite size effect, which you don't have probably in here, okay? Anyway, in the system in Houston, okay, basically we have a BEC made of one single traveling wave optical dipole trap, which is able to trap regularly 8 × 10⁵ atoms. And it has a very elongated aspect ratio. So it basically tries to mimic a 1D system. So you see there's a very large aspect ratio here, or small if you like, depending on how you divide it. And this time, the idea was really play directly with the interactions through the magnetic field, but modulate. So basically, we set the system, we make the condensate, we modulate for a small time, typically like 5 milliseconds, with a small amplitude, and hold for a little while so the extra excitations, they damp out, so we see only what is really standing in the system. So we see these nice patterns here, which stretch all the way along the condensate. And they last for a little while, so it's good for studying because you can really see the dynamics and see how it goes on. In the process of understanding these results, we came across this theoretical framework proposed by Nicolin a while ago, basically on a variational approach, together with the Mathieu equation for the solutions, basically an oscillator for omega I, which drives the growth of the amplitude, essentially. And what is, well, to make the long story short, we find two modes which are more, we find a bit more, like 3 or even 4 modes from the theory, but in the lab we were only able to identify these 2 modes, which is called the Faraday wave and the resonant wave. I will explain a little bit more along the way, okay? What we mean by them. Exactly. Exactly. Very good. So you understand, right? So one, it will, yeah. Defocusing? What do you mean? Yeah, for now, yeah, exactly. Because the other side will complicate a little bit, so we decided not to go much in there. Yes, check. So that was basically it. We ramped this B field and tried first to find out a bit more, which was, sometimes you see a little change in here in the conditions. The conditions of the BEC were changed depending on the region or the range of frequencies we were studying, just to make the contrast a bit more visible, okay? But that won't affect the overview of the problem. So here we have a typical shot, okay? Sorry for the poor quality of the figure here, but basically that's it. It's pretty much, it's very similar to what the people saw before. We decided to take the Fourier transform of that and to see what kind of spatial frequency we have. And we were modulating around here. So if you remember, the trapping frequencies were 476, so typically 950 hertz is where we were scanning around here to see this regime. Actually, it's a range in between 500 and 1 kilohertz typically. We can go a little higher too. But basically, this spatial period here, which is clearly seen in this peak, it was predicted exactly or nearly exactly by the theory. We got very happy with that and decided to continue to scan the range to see if we saw a bit more. So instead of just studying the parametric resonance around this range here, we decided to go on resonance and see what we could see. So at this range here, we started to see a second peak, okay, which is the secondary or resonant mode, as I was saying before, okay? And they appear up to the resonant frequency. So in this case, the dominant mode is really the resonant frequency of the trapping, the radial frequency, okay, which is the faster. From there on, you stop seeing this mode, okay, the secondary peak, and you only see the large peak here, which is the primary. But it's directly seen from the image. It's not, there's no really a need for super processing of the data to see clearly what's going on. And again, this the Nicolin's theory, it's really right on. I mean, there's no adjustable parameters. Basically, you just put the trap conditions there, and number and everything, you get it. And so we're very happy with that because it's not a complicated thing. We decided to go a little further and to study how the theory will support the dependence on the interactions here, which is basically multiplying the line density by the average interaction here, the scattering length. And we scan it around this region here, which is around here, okay, this region. And again, the theory predicts pretty well on here. And I mean, we'd say that it's a very good agreement with such a simple theory. I mean, we were really, really happy to go on. So we decided to continue a bit more and see now, okay, one thing we saw during the experiments, which to see the dynamics of this mode. So you turn on the modulation around this range here. We just live a little while, and we see that this Faraday pattern, it emerges on top of the BEC, okay? So, but how it emerges and how it lasts over time, and this was interesting to see. So we decided to map or to follow the peak around here, okay? This dominant peak, and see how it goes, how it behaves as the whole time goes on. And we start to see growth, and then the decay, and then it grow again, decay again. So we thought what might be going on, and we decided, okay, let's try to follow one of the Thomas Fermi radius of the condensate, in this case, the long Thomas Fermi radius. And we saw that, okay, it was oscillating too. So there was an interesting result. We were not sure that we were going to find that. Basically, there's a coupling in between this Faraday wave, or this parametric resonance, and coupling to this quadrupole on the actual mode, okay, on the actual dimensions. So, and it oscillates in about like 100 milliseconds here, you'll see, which is typically 8 point something hertz, which is pretty much described by this simple formula here, which is being known for a while. And again, this, okay, we decided to investigate a little further about this rise, you know, this fast rise here. And then to do so, basically, we took a Gauss-Pitoevsky equation and decided to plug in the values of our BECs, and decided to see how it goes over time to see if it fits well here. And okay, and we were thinking mostly about the actual size. So you will see here there's many oscillations here. These oscillations are due to the radial dynamics. But if you ignore them for a little while, just think about the overall trend or the envelope of this curve, you'll see that the growth here is pretty much exponential. And it was captured by the simulation, very much as we expected. The rise time is about like 3 milliseconds, and it's pretty much exactly what we saw in the experiment. Furthermore, we decided to check what happens in the radial side. So basically, you see it grows and very quickly here, and in the same, let's say, time, you see it reach a maximum here, and then it goes and kind of damps a little bit here. We decided basically, well, what we see here is that that's the typical thickness of the BEC. So you cannot go beyond that, okay? This small size here. So it can only grow up to there because there's no matter to grow, and so it has to stop, and it's eventually damped out by that. And if we take the results of this simple simulation using the GP and put on the top of this data, which you saw first here, and I repeat in here, it's right there. I mean, it's no trick. So I think by now we understand pretty much what we saw in the lab, and we're pretty happy with that. Even the spatial frequency here is captured, so it's pretty a pretty good result for now. So now, for those of you that are kind of, yeah, sure. Yeah. This one? That's pretty good. Those are, it's ongoing, okay? We didn't do that much time before, so we still have to think. We just got happy that about the basic results, you were right about it. But we decided to verify, and we didn't find this kind of study in this previous work, so we decided to go a little further, and that's so far as we went. So, but thanks for the hint. I mean, we continue on that, and hopefully we'll be able to ask you more directly. But okay, but this is the one range of this frequency dependence that we study in amplitude. So small amplitudes and twice the trapped frequency, it's what you get, Faraday waves, and that's somewhat not so much interesting. So we thought it was pretty cool to see it and study it for a little while. But there's the ongoing of this experiment, kind of, we went to a different range, different regime for lower frequencies, even lower than the ones I showed you before. And this is what we're going to see after. Okay, so I'm going to talk a little bit about this off-resonance towards a lower range here, okay? We were actually from like 10 to 70, 80 hertz now, modulate. And if we keep the same experimental conditions that we did before, we won't see anything in here, okay? We started like that, and there was no fun at all. There's no results to report or anything. So we decided to increase a little bit the depth of the modulation, and also to last longer, forgive me. So in the previous experiments, we were exciting for or modulating for about 20 milliseconds, okay? Now I'm going to go like 10 times that, up to 250 milliseconds. So I have to increase the amplitude a lot, and I have to make it last longer. So we were really like beating this BEC very hard, if you think so. And in that case, this is the typical images we see now as a function of the whole time here. What was impressive to us was like these patterns, once they form, they are very stable. They can stand up to 4 seconds. That's kind of the maximum we can go in the lab. But it's a pretty long time for a atomic. Yes.
4 seconds after stopping.
Just waiting in the trap. So you see, we still were able to see. And what it strikes us is that, okay, now it's completely different. There's no regularity here on the size of these blobs or bubbles, if you like, and the distance in between them is not regular anymore. I mean, there's all kind of different. That's why we started looking and studying a bit and going after the granulation, okay? But anyway, as a first start, what we did was we decided to see what the Gauss-Pitaevsky equation can give us using these conditions here. And it really doesn't fit. It doesn't do the trick. It fails, let's say to speak. It's much more like a Faraday wave or something very reminiscent of that. So it doesn't capture what's going on here. And then, so it's a collaboration. We look for one of our postdoctors, a former postdoctor, Mario Tsatsos, and his colleague from Austria, Axel Lode, and they decided to look into that. And they came across this different method or theory, multi-configuration, time-dependent heart rate for bosons, and especially the single shot technique. And I won't show the pictures anymore, just the densities here. But I mean, once we decided to check a little bit if we can run that in a one-dimensional and see what we get compared directly to the lab results, we started to see an impressive agreement to the overall shape. In the theory, it's very random, just like in the lab runs. So it's probably, you'll never be able to see exactly the same profile in 2 shots of the lab and also in this theory. But so we decided just to use other tools to even go ahead and see what they go. So and then we started really calling these results as granulation. So we decided to use one of the definitions we find in the literature for that, which basically has to do with this random size and random distances in between these blobs of condensate. And that so far was the only theoretical framework that could recover that for this particular experiment. More like speckle. Yeah, in a sense, yeah. Yes, like if we continue, if you hold in trap, that's what you see, right? It changed how it distributes. It really changed. If you look at the line profiles, you will see, you will see that this thing will change a little bit here. The amplitudes, the peaks and valleys, they will change over time. So for that, Vanderlei came with this idea of how can we kind of create a method to try to see if we can see where these things break apart or so, because it was pretty clear that there was some sort of threshold in the region of frequencies where modulation goes from 0 to 70, 80 hertz, or even beyond, like 100, that it was pretty clear that we reached this condition where the pattern, this distribution, these granules, these bubbles, these blobs of condensate, kind of was they were clear and they will last a lot for a long while. And that was basically just take the Thomas Fermi fit here, take the difference in between the line density and the Thomas Fermi, the ideal Thomas Fermi for that, divided by the Thomas Fermi to basically normalize that. And then we started to see how we can use that to see. So in this theory, they use like a multi-orbitals to understand a little bit and see if they participate. And that's where they got the edge on the explaining the results. Basically, by doing that with this contrast function, we started seeing that these orbitals, they start to emerge and to play an important role here around the same frequencies where if we do the same procedure for our real data, I mean, it's dead on. There's a small shift here comparing the experiment with the many-body theoretical framework. And even though it's not exactly on, qualitatively, it agrees pretty well with what's going on based on this contrast function. So it was interesting to go on a little bit and see what the theory shows or predicts when we're above and below this sort of a critical or frequency. There's not a critical frequency. As you can see, there's a small range in between 40 and 60 hertz for this experiment. But we decided to stick around like 20 hertz here and 80 hertz to be away, a little bit away from the threshold, okay? So that's pretty much what we see here, okay? If we study just the line density, how it behaves, we can see that it also lasts, so we modulate for a little while, and then we stop and hold for another while, okay? In this case, we were not holding for too long, but anyway. What is important here is that this framework really show that at some point, really, you needed more orbitals to really understand what was going on here in any case you look for, even if you look for correlations or something like that. So the theoreticians, they got pretty happy because it was one of the first time that they had an experimental result to play with and to try to match, and they think they're very happy with that agreement so far, even though it's, to us, more qualitative than quantitative. Anyway, so to finish, to wrap up, basically we use this modulation of interactions under different scenarios, and I'll try to give you an overview. Basically, if you use resonant with collective modes, this is pretty much what you see. In this case, in this quadrupolar mode, coupled to the actual mode, if you go non-resonant, you start to see interesting things like granulation of a BEC, where this have random patterns of sizes and distance in between those separated islands of condensates. And I mean, this adds up to the sort of pattern formation that people has been observing worldwide. For instance, in Chicago by Chengqing, where you have also a driven 2D BEC with these jets of BEC being emerged. So, and previously, in the same group, we have this soliton trains observed, so it's a different physics here, and also quantum droplets, which is from Stuttgart. So basically, that's it. That's the scenario for now concerning the pattern formations in BECs, and I thank you for your attention. And this is where I finish. Thank you. Yes? Should I give them this or no? Okay, cool.